In section 4.5, we're going to talk about the modeling of exponential growth. And modeling basically means taking some real-world data and making an equation out of it. In contrast, most of the time we get an equation that's an exponential function. So we get f of t is equal to some number and then e raised to the kt, and we're told plug in some values of t and then you can calculate the function value. But when we do modeling, what we're trying to do is we create the formula given the shape or a few data points. And whenever the data points indicate that the amount is increasing, that will be a growing exponential function, and then we will have a positive k associated with that. K is greater than 0. If we see some points where the numbers are decreasing exponentially, then we would assume then that k was going to be negative. So when we create our equation, it says just as you can find a linear equation from 2 points, it's possible to find an exponential equation from 2 points. So in a linear equation, we have y equals mx plus b, and x is the input variable, y is the output or the dependent variable. But what we're trying to do is find constants for m and b by using those 2 points. When we are finding an exponential equation, we also have our input variable x in this case, or we sometimes use t, but we also have our output or our dependent variable y, and the constants that we are trying to find are this a0 and then also k. So by plugging in specific points, we hopefully should be able to find those 2 values and then make an equation that's based on x and y. So let's read this information. It says in 2010, that's an important number, the population of Colombia was 44.2 million, and the population is projected to be 62.9 million in the year 2050. And the question is, what is the growth rate k? So we are trying to find that value, and to do so, what we want to do is put the year as the input value. Now these numbers 2010 and 2050 are not convenient numbers to use as our inputs. So what I'd like to do is have x's that correspond to those. So the year 2010, I'd like to let that be when x is equal to 0. So that's my starting time. And then in the year 2050, that's going to be 40 years later, or when x is equal to 40. If I use these values, then it makes the calculation simpler. Next, I'm going to go back to the format of the exponential equation, which is y is equal to a0 e raised to the k times x. Now let's plug in some values of x and y to see if we can solve for those constants, a0 and k. So when x is equal to 0, that's the year 2010, and we see that the population is 44.2 million, and I'm just going to express y in terms of millions. I'll come back and adjust for that at the end, but I'm going to say y is equal to 44.2. And let's see what happens when we plug in here. When I let y equal 44.2, I get that this is equal to a0, e to the k, but then times 0, and k times 0 gives us 0. So this is just going to be e to the 0, which is 1. So this is equal to a0. So we can update our equation now, plugging in for a0. We get y is equal to, and now we've got a number for a0, which is 44.2 e to the k times x. Now if we want to find k, we'll need to plug in some values of x and y, which are different data points than what we have, and thankfully we do have a second data point. We've got that when x is equal to 40, then that y is equal to 62.9. So I will express that over here at x is equal to 40. We get then that 62.9 is equal to our 44.2. and times e raised to the 40k. And I know this is a little bit cramped here, but let's complete the calculation. If I divide both sides by 44.2, we've got 62.9 over 44.2 is equal to that isolated exponent, e raised to the 40k. Now to isolate the k, we need to take the natural log of both sides, and so I've got natural log of this fraction, which I've calculated as 1.423 by calculator, and this is equal to 40k, so natural log of the right, and again the e and the natural log will cancel out, so I end up with 40k, again taking natural log both sides. So when I solve for k, I get that k is equal to this natural log on the left, which is 0.353 approximately, divided by 40. And when I simplify that value, it comes out to be about 0.0088. So I'm going to plug that back into the original equation. So the first thing that we have done is we did find k. The second thing is when we want to find the population in the year 2030, what I should do is rewrite this equation with all of the constants that we found. So we said that a0 was equal to 44.2, so I'll write it as y is equal to 44.2, and then e to the kx. E to the k we said is 0.008, and then x. Now when we want to find in the year 2030, realize that the year 2030 is 20 years beyond the year 2010, and so x is going to be equal to 20. And when we plug that into the equation, we get y is equal to 44.2 e raised to the 0.0088, I lost a digit there, and then we'll multiply that times 20. And if we perform this calculation, the exponential portion comes out to be about 1.193. So when I completely simplify this, it's about 52.7. And that comes out to be in millions because we have been expressing our population here in millions, so we have to be aware of that. The third question is, in what year would the projected population be 70 million? So we can see that with this graph, it is increasing year by year exponentially. 70 million, I'm going to just choose this and realize that our population is expressed in millions. But that is our y value, so I'm going to put it on the left side of the equation. 70 is equal to, our constants were 44.2, and then we have e raised to the power 0.0088, and then times x, which in this case is what we are trying to find. In what year? So that's what we are isolating, is x. Again, we need to first isolate the exponential expression. So we divide both sides by 44.2. So this exponential expression, e to the 0.0088x, is equal to about 1.584. And if we take the natural log of both sides, we can eliminate the e, and this expression then will be divided by 0.088, and we get then that x is equal to about 52. What that corresponds to is then the year, 52 years out from the year 2010, gives us the year 2062.